Welcome back to the course Mechanics of Solids. So, as we have seen in the last lecture, we are discussing about the truss, plain truss, and we are talking about that how the truss is formed and what are the different say specifications or different say details of the truss members. So, anyway, so we are just basically covering this chapter. So, free body diagram with examples on modeling of typical supports and joints, conditions for equilibrium in 3D and 2D, friction, limiting and non-limiting cases. So, these are the things we are discussing right now. So, let us talk about the truss. Let us go back to the discussion where we left out in the last lecture. So, basically in the last lecture already we have seen in the truss, right, we in this particular subject we are including only plane truss, as we have decided in the last lecture. We are not talking about the space truss. Okay. Now, the external, I mean in the last lecture we stopped here, the external loads whatever are generally applied on the truss, they are assumed to apply at the joints, and we have seen in the last lecture that how the joints will look like in the real life, right. So, whenever you have one member in the truss, basically the truss will be having two joints means two ends, right. That member will be having two ends, that is a linear member. So, there will be two ends and those two ends will be connected to some joints. So, whenever some external forces are applied on the truss, so those forces are applied on the joint. So, that is our basic assumption and we will be analyzing the truss based on that assumption. So, we are not considering any load, any externally applied load which is applied in between the member. Okay. Now, the next point to be remembered, that is truss members are two force members. Okay. So, truss members are two force members. Now, already you know from our previous discussion that what is known by two force member, what is known by three force member and all those things, right. So, truss members are two force members. Okay. So, that is the basic thing we need to remember for any member involved in that truss system. So, when we are considering the member, any member is two force member, then of course, it could be either tensile member or compressive member. So, now basically this is one member, say this is one truss member, okay, as you generally see in the real life. So, it could be either tensile member, that means it is carrying only the tensile force, or it could be compressive member like this, only the compressive forces. So, and these forces are of course equal and opposite from the two force member details whatever we have covered in the previous lectures, right. So, either it could be tensile, that means this one, okay, equal and opposite forces are acting, okay, or this could be like this, compressive. So, apart from these two, tensile and compressive, we cannot have any type of members, because this is the two force member. Okay. Then next point is apply half the weight, self weight of a member to each of its two joints. Now, we need some discussion for this. Suppose every member or whatever members are there in the truss. So, every member has got some self weight, right. But generally the truss is designed to carry a load such that the self weight of individual member is very negligible as compared to the externally applied load. So, therefore, most of the times we will see that most of the times we generally neglect the self weight, because that is as compared to the externally applied load is very negligible. So, that is why we generally do not consider, but frankly speaking, if you want to analyze the system in the right say direction, so basically you need to consider the self weight of the member also, which is applied as external force on the member. So, when you have this kind of situation, so this is your member, okay. So, this member is having two ends, of course, two ends will be connected to two joints basically when it will be forming a truss. Now, the self weight W, if you have, generally we can assume the self weight is acting at the center of gravity of the member, but as we have already decided that no force will be applied in between the member. So, we will just distribute this force half of W at each end. Okay. So, this is our idealization, you can say, if you consider the self weight of the member, but most of the times we will not consider the self weight of the member unless until it is mentioned. You also do not consider the self weight of the member. Okay. As I told you that self weight of the member as compared to the externally applied load is very negligible. If you think of the truss, okay, truss bridge for the railway track, now the load of the railway, I mean rail, or the load of the train is much more higher than the self weight of the member. So, therefore, we can neglect. So, for the idealization purpose we can neglect, but if you want to do the proper design or the proper analysis, you need to calculate or need to consider the self weight of the member, and that can be considered in this way. Okay. Now, we will be talking about a concept, just rigid concept. So, it says if the removal of any of its members destroys its rigidity. Now, what do you mean by rigidity? So, when I am saying the truss is, I mean fairly rigid, what do you mean by that? Rigid means stable. Now, if you look at this truss, which is made of three members, okay, and there are three joints, say this is your hinge support, this is your roller support, that means it will form the simple support, right. So, if you consider this elementary truss made of three members with three joints, you see this truss, I can say this truss is just rigid structure. Okay. This truss is just rigid structure. Why? Now, if you apply a load here, okay, it can carry the load without disturbing the stability of the structure. Instead of having the vertical load, you may have some horizontal load. Still, the truss will carry that horizontal load, and of course, these loads are well below the strength of the truss, actual truss. Okay. So, if you have the horizontal forces acting, still the truss will carry the load, right. So, it will carry the load without disturbing the stability of the actual structure. Now, if I remove one member, okay, if I remove one member, now what will happen? Is it a rigid structure? That means, is it a stable structure? Of course not. So, under the action of this load, this member will try to rotate. Okay. Under the action of this load or the horizontal load from this side, this member will try to rotate. So, the stability of the system will be getting disturbed by the application of the external loads. So, this structure we cannot say it is a rigid structure. Okay. So, now I mean earlier when you had the member, when you had the just rigid structure, that means another member was there, at that time if you apply the load there will be no rotation or there will be no instability in the structure, but as you have removed one member from this, immediately the instability is coming into the system and rigidity is getting disturbed. So, this kind of system is known as just rigid structure. So, it says that if the removal of any of its members, I have removed only one member and that basically disturbs the stability, right. So, if you remove any of its members and if it destroys the rigidity, then that is known as just rigid structure. Suppose for example, if you consider a truss like that, okay, some square shape or rectangular shape or whatever. So, these are all joints. Okay. Can you say this is a rigid structure? Yes or no? Of course not. This is not a rigid structure. Suppose what will happen if I apply load in this direction, this will try to rotate, this will try to sway in this way, or if you apply a load in this direction, it will try to sway in this direction, right. So, this under the action of the externally applied load, basically this will not be stable. So, that is why this system is not a rigid system, right. But for the sake of completeness of the discussion, if I add one member here, now what will happen? If I add one member here, what will happen? It will be rigid structure, right. So, how many members are there? 5 members now. So, 5 members are making this system as a rigid system. Immediately you remove this member as it was there earlier, the stability gets disturbed and it becomes unstable, right. So, rigidity is getting disturbed by removing only one member. So, if you connect this, that structure was just rigid structure, and now after removal of your rigidity gets disturbed. Okay. So, similarly, we will be having another kind of, so it is not necessary that all the times you will be getting just a rigid structure. That means, if you remove one member, immediately the system will be going to the instability. So, most of the times it is not the case. So, most of the times you will be getting over rigid structure. So, if removing a member does not destroy rigidity, Okay. If it does not destroy the rigidity, by removing a member, if you remove a member, if it does not destroy the rigidity, then basically the structure is known as over rigid structure. Okay. So, now the obvious discussion what is coming from this part is that what is my basic structure which will tell me this is the rigid structure, right. So, what is our basic structure or elementary structure which will be the rigid structure. So, for that we can simply write the most elementary just rigid truss is one with 3 members connected to form a triangle. Okay. The most elementary, already we have seen that with 2 members. If you look at the previous example, with 2 members it was not rigid, it was not stable, right. Immediately you connect one more member which will form a triangle, that was giving me the just rigid structure. So, that is basically the elementary structure which will be the just rigid. That means, for getting just rigid structure, the minimum number of members should be 3, which will be making a triangular pattern. That will be your elementary truss. Okay. Now, for how you will identify that whether it is just rigid or not. So, there is some law. So, for just rigid plain truss, okay, your m equal to twice j minus 3, where m equal to number of members and j equal to number of joints. Okay. So, if this equation or this relation is getting satisfied, then you can say this is my just rigid structure. Now, let us check with the 3 member system which will be making a triangle. I am not showing the supports, it is quite understood that of course support is there. So, this is your elementary just rigid structure, already we have decided. Now, let us talk about or let us see that whether this equation is getting satisfied from this elementary truss or not. How many joints are there? J equal to 3. So, in this equation, if you come in this from this equation, what I get? So, j equal to 3, that means number of members must be 3, right. So, in this triangular say truss, basically your m is also 3. So, it is satisfying this expression or the equation, therefore, we can say this is the just rigid structure. Now, let us talk about 2 members. This is one member, this is another member. How many joints are there? 3. If you put in this equation, then how many members you should get? 3, but you have only 2 members. So, therefore, it cannot be the rigid structure. So, this is a check by which you can check the rigidity of the structure. Now, talk about that this kind of truss, square or rectangular orientation. How many joints are there? 4. Okay. You have 4 joints, 4 corners means 4 joints. So, if you put in this equation, then basically how many members you should get to get the rigid structure? 2 into 4 8 minus 3 is 5. So, minimum 5 members you need to get the just rigid structure, but how many members are there? 4. Therefore, it is not the rigid structure, and already we have seen that, already we have proved this is not the rigid structure. So, if you connect one member, then it will become the just rigid structure. Okay? Understood? Fine. So, with this discussion, now we are going to find out determinate truss, statically determinate truss or indeterminate truss. So, let us talk about that thing first. Already we have seen in the last lecture that what is statically determinate member and what is statically indeterminate member, and now we are going to see that thing from the truss. So, suppose this is one truss, you have load here say F1, A, B, C. Okay. One thing is already from the previous discussion, one thing is very clear, this truss is rigid truss, but whether it is statically determinate or indeterminate, that also we have to look at, otherwise how we can solve the support reactions. Now, if you remove the supports, if you want to draw the free body diagram, just remove the supports. So, you will be getting AX, AY if it is your XY say plane, okay, and you will be getting CY. Okay. So, these 3 are your unknowns, unknown support reactions. So, you have 3 equations of equilibrium, you have 3 unknowns. So, you can solve it. So, this is your determinate, externally determinate structure, right, as well as if you look at the members, I mean say suppose if you come to this joint, basically if you want to draw the free body diagram of this joint, okay. So, from the equations of equilibrium you have got the magnitude of Ax, Ay and Cy. So, now they are known to you, they are not unknown. So, if you come to this joint A, okay. So, you have, because AB is a 2 force member, AC all members are 2 force members, it could be either tensile or compressive. Okay. So, if you consider the free body diagram of this particular joint, what are the forces are acting on that particular joint? AX is acting, AY is acting, member force AB is acting, member force AC is acting. So, member force AB and AC both are unknown to you, you do not know. What are the things known to you? You know AX and AY. So, at this joint basically how many equations of equilibrium available with you? Because at that point, if you consider a point, your moment equilibrium is not coming, because that anyway if you consider the equation moment equilibrium condition here, it will be giving you the trivial solution, right. So, that I do not want, I want some non-trivial solution. So, at that joint basically you have only 2 equations of equilibrium available with you. What are those? Summation of f x equal to 0, summation of f y equal to 0. right, summation of f x equal to 0, summation of f y equal to 0. So, these two equations of equilibrium are available with you at that particular joint. So, two equations of equilibrium are available with you and there are two unknowns. So, you can solve it. Similarly, if you come to this point joint C, how many unknowns are there? Two member forces, member AC and member BC. The forces in those two members are unknown to you, say for example, Cy is known to you. How many equations of equilibrium available with you? 2, summation of f x equal to 0, summation of f y equal to 0. So, therefore, conceptually I can get the values of member force AC as well as member of BC. So, based on this discussion we will come to the solution procedure for any particular truss. Now, similarly, if you consider if you consider joint A, you have got member force in AB, member force in AC. Similarly, if you consider joint C, you have got member force BC and member force AC is already obtained. So, all the forces in individual member have been obtained. So, by just exploiting the equations of equilibrium. So, by exploiting or by satisfying the equations of equilibrium, if you can solve all the member forces, so that is known as internally determinate truss, right. Similarly, if you look at this truss, let me draw it. You have support reactions AX, AY, this was hinge. So, and you have roller support here, so only CY. This is A, B and C, and you have so how many members are there? 1, 2, 3, 4, 5, 6, 7, 8, 9. So, there are 9 members, okay. And if you just follow whatever we have discussed now, you will see that all the forces in all the members cannot be obtained by just satisfying the equations of equilibrium. This kind of structure is known as of course, I mean for this structure we can find out. So, for this structure we cannot find out. So, this is also statically or internally determinate. Okay. This is also internally determinate. So, you can see that, you can check it, internally determinate. This is also internally determinate. So, if we apply any force here, say suppose this is one force F is applied here, and under the action of these forces you can find out the forces in all the members. So, therefore, this structure is also internally determinate like this, though it looks like very complicated, but you can solve it, and we should know, and we will be coming to that part right now, that how we can solve this member forces. Now, if you have this kind of say truss, here also you have say AX, AY, this is point A, this is point joint B, this is joint C, you have CY, okay, and a force is applied here F1, okay, at joint B. If you look at this structure, you will find out that you cannot get all the member forces by using your simple equations of equilibrium. So, therefore, it is known as internally indeterminate. Now, why I am using internally and externally, why this word is coming out? Say if I can find out all the support reactions, then that is externally determinate, and if I can find out the member forces by just simply using the equations of equilibrium, then that is known as internally determinate. So, externally determinate means if you can manage to get all the support reactions, internally determinate means if you manage to get all the member forces. Similarly, this structure is also externally determinate as well as internally determinate. This structure is externally determinate, but internally indeterminate, because you can find out all the support reactions, but you cannot find out all the member forces. Well, so I will stop here today. So, in the next lecture we will be talking about how to solve or how to analyze the Truss system. Thank you very much.